Okay, welcome in this second recording regarding the intercept method. I've told you last time that the intercept method is all about comparing actually your true altitude and your calculated altitude of a celestial body. If you determine the difference between the two of them, you get delta H, and delta H is your intercept. Okay, HC is calculated via this formula here. The sines of L and declination will determine whether you have to add or subtract. HV is an observation that you get from your sextant. Okay, delta H can be positive or negative. Positive, then it should be marked towards the true bearing. When it's negative, it should be marked away from the true bearing. Okay. Voilà, and so this is what you end up with on the drawing. So you have on this drawing here your assumed position, which is this one here. This compares to LE and GE. Okay, and so starting from this true position, you can make 3 observations, and for each and every observation, you determine the true bearing. Okay, the true bearings are the blue lines that you see here on this drawing. Okay? And then starting from these true bearings, what do? You indicate from your assumed position, you indicate the intercept, which is this one here, that one there, and this one here, okay? And so for this first case, the intercept will be positive because we will mark it towards the true bearing. Two ways, contamination of both, but in this case, it is towards the true bearing, okay? For the other ones, we do the same thing, and then we perpendicular to our true bearing, we mark our lines of position, which are these one here, this one here, and that one there. And what do we get then? Then we get a triangle here, which we call a cocked hat, and we can assume actually that is what's mostly done. We'll talk about that later on, but that is what's mostly done. Sort kind of the center of gravity of the triangle will be the cocked hat. This will be your true position. Okay, but of course, when we do these observations, we always make errors. Now, when we do the intercept method in observer's position, will always be the intersection. I told you that you need at least 2 lines of position. When you do 2 lines of position, it's very easy. The intersection between the 2 will be your position. But of course, when you do 3 observations, you get 3 lines of position. And so when you are very lucky and very good in sextant observations and calculations, you get the lines of position intersecting this way at exactly 1 point. Okay, but unfortunately, most probably, you will end up with something that looks more like this, okay, which we call a cocked hat. Okay, we have here 3 lines of position forming a triangle. So now we need to determine where we are somewhere here in this triangle. Okay? They call this triangle a cocked hat, similar to the hat that you see there. And so when we want to determine our position in the cocked hat or in the triangle, we can say that when the observation azimuths are spread over more than 180 degrees, the most probable position would be inside the cocked hat. But depending on the errors we make, we only have a probability of 25% that we will be exactly on this spot somewhere in the triangle. Okay, voilà. Now, normally, as I already told you, the 3 lines of position of the 3 observations that you have done, they don't intersect at a certain point, at 1 point, but they form a triangle due to what? Due to our errors that we make in our observations. Okay. Now, when we talk about errors, there are 2 types of errors. First of all, we have systematic errors, which can be predicted. They follow a certain pattern, they follow a certain system, and so they can be predicted. Okay, this is something like the uncorrected index errors of your sextant, which is one of the errors. It's represented by I, as I told you. It is always something that you need to add when you are transforming your instrument height to the true altitude of your celestial body. Okay. Of course, you also have your personal errors that you make. People always have the tendency to always under or overestimate the celestial body's altitude. So also this can be considered as a systematic error, because normally you always tend to follow the same rule. You always tend to have the same over or underestimation of the celestial body. Okay. Unfortunately, there are also random errors. Okay. They are unpredictable, and they are governed by, this is just something very complicated, the laws of probability. They depend a little bit on the observer's experience and also on the observation conditions. Okay, what is the quality of your horizon? Is it very well depicted, or is there something like a very unclear zone to determine whether whether the horizon stops and the water begins? Depending on the stability of your ship, is your ship rolling very much, moving about? Or it can also be influenced by abnormal atmospheric refractions, which is not included in the nautical envelope. Okay. Now, normally, when you have no random errors and your azimuths are spread over more than 180 degrees, then systematic errors, which are predictable, they can be eliminated. Okay. The true position is considered to be the cocked hat. In this case, only when the observation azimuths are spread over 180 degrees. Okay, so you have here an estimated position. This is your EP. Starting from that estimated position, you have a bearing number 1, let's say, bearing number 2, bearing number 3, and then the blue indications here are your intercepts. Okay, and so this gives you 3 lines of position, being the red lines or the orange lines that you can see here. Okay, so what do you finally end up with? You end up with the cocked hat that has this form. Okay, now if we, I think I'm not thinking. I think I said I used the wrong terminology here. They say that the blue line is actually the systematic error correction. Actually, this is an error correction which is supplemented on your delta H, in fact. Okay, so what can you do? Starting from your assumed position, you actually have your delta H corrected for systematic error. Okay, being an uncorrected index correction or an over or under estimation of your altitude. This would influence delta H. So you have here the corrected delta H, which you apply here, and then this will give you your lines of position. Okay, if your azimuths are spread over more than 180 degrees, and when there are no random errors, then the systematic errors can be eliminated by applying a correction to your delta H, and then you can assume that this here would be your true position. Okay. Of course, when you have no random errors and your azimuths are not spread over 180 degrees, then they talk about an outside fix, meaning that your true position will not be in the cocked hat, and that the corrections that you apply here, these ones here, will cause your true position, being this one here, to be outside of the cocked hat. Okay, because of the direction towards which you have to displace your line of position in order to correct for the systematic error correction on your delta H. Okay, voila. So lines of position need to be corrected by moving them backwards or forward for the systematic error, and so this means that your intercept will change. Okay, in systematic error, remember again, this was either the over or underestimation, but it can also be the index correction. Okay. But then, of course, systematic errors, they can be corrected, they can be predicted, but things get even worse when you have random errors. Okay, when there are random errors, you only have a probability of approximately 25% that you are somewhere here in the cocked hat with a spread of when your lines of position, when your azimuths, it's the same thing, have a spread of 180 degrees. Otherwise, it gets even worse. Okay. Voilà. Now, when we talk a little bit about random errors, when you take several measurements of a celestial body subject to a random error, the error values are distributed. This is statistics. This is statistics course. They are distributed around a mean value. Okay. And the normalized curve of any type of random error is symmetrically centered, as the one you can see here, around the mean value. Okay. And then the probability of any similar observation having any given correction can be, any given error can be calculated. Okay. An important characteristic of probability distribution here is the standard deviation, which is called also sigma. Okay. Normally, when we talk about this is what you see here, the standard deviation, it can be calculated by this formula. When you have centered around the zero error value of your curve, when you have one time the standard deviation on one side, and one time the standard deviation on the other side, you have 86% probability of your error being within this area. Okay. If you take 2 times the standard deviation, this will give you 95%. 3 times this will give you almost 99.7, almost 100%. Okay. Now, the standard deviation, this is something that you have seen in the statistics course. It can be calculated by this formula. So you have first the number of data points, then you have the value of each data point. You have the mean value of all your observations. And then if you calculate this formula here, if you take the square of the sum of all the differences between the value and the mean value, to the second power, or I don't know how to say this in English actually, this is the first time. And then you divide it by the number of data points minus 1, and you get your standard deviation. Okay. Voilà. Now, in most cases, when we want to determine the true position in the cocked hat, it's an adequate solution to choose the true position in the cocked hat as being, as we did in the exercise that I showed you earlier, the triangle, the center of the triangle. Okay, but if you want to be a more precise and more sophisticated, and you want to do a more sophisticated analysis, you may also want to exclude the influence of random errors on your position. Okay. Now, then we have two situations. The first situation where all lines of positions are of equal quality, meaning that they all have the same standard deviation. The second is when one line of position is better than another. Okay. When we are in this first situation, there is a mathematical way of determining your position in the cocked hat. Most likely position will be located at the C-median point of the triangle. Okay. How is the C-median point of the triangle calculated? If this is your cocked hat, what can you do then? You have here the middle point of every side of the triangle. Okay. For each triangle, for each angle of your triangle, you can determine the bisector, which are these lines here. I will take purple. These are the bisectors. Okay, you can do this for every angle. And what do you do then? You simply just reflect the median point here, perpendicular over the bisector, and then you find here point D accent. Okay. If you then take that point and bring it to point B of this triangle here in this case, then you find the C-median. Okay, we can do this for all angles. Okay, and so our most likely position will be then here the intersection of the 3 C-medians, or they also call it the Lemoine point. Okay, that is when all observations have the same standard deviation. Okay, but it can get more complicated if there is no uniform standard deviation. Okay, what should we do then if there is no uniform standard deviation? We should consider actually the lines of position not as really this simple lines of position, being, I will take another color, being this simple line here. No, we should consider it as bands of position. Okay, not bands of brothers, but bands of position. And for this line, this will be here, this band here, going from 2 times the standard deviation on the one side to, from the standard deviation from the one side to the standard deviation on the other side. Okay, and you see here that for all 3 observations, for the first one, the standard deviation is 1, for the second one, it's 2, and for the third one, where is it? It's 3. Okay, and so in this case, we will need to take into account the influence of the standard deviation on our determining of our position. Okay, our position in the cocked hat. In this case here, according to the system that I will explain to you, we find that this is our true position in the cocked hat and not actually what we would more expect this point here. Okay, now there are online tools for calculating lines of positions, and what are they based on? They are actually based on a system or some form of system that I will explain to you now. Okay, now what do we do actually first? The most likely position is the one that we have calculated here. The result for the most likely position is determined by what you see here. Okay, P is the most likely position. It's the coordinates of the most likely position, and I will show you this already. If we fill this out in a spreadsheet, we find that our final position will be this one here. Okay, so this here corresponds to this here. Okay, now what do we do? If we have a cocked hat, I will go back to my blue color. This is our cocked hat. Yeah, more or less. I will use the blue like this. What can we do? We can determine the sides, the length of the sides. Okay, the first side has a length of 13, or this side has a length of 13, this side has a length of 10, and this one has a length of 9. Okay, so we take 10, 9, and 13. Okay, then we take our standard deviation to determine the Q in this formula here. Okay, now the Q, what is it? It is the length, which is this one here, multiplied by the standard deviation times 2. Okay, again, this is, I will quickly look this up, the kwadraat. How do you say this in English? This is a little strange. You know what I mean? Give me a little time. Kwadraat. I'm sorry for this. In English, translate, it's the square. Yeah. And the other one is the root, of course. I'm sorry. So we take the square of the length multiplied by the standard deviation. Okay, and so this gives us a value of 100 for this first, 324 for the second, and 1521 for the third. Okay, I'll erase this again. Okay, so this corresponds here. This here corresponds to A that you find there. Okay, what do we do then? We divide it by the sum of all A's. Okay, so we add 100 plus 324 plus 1521. This gives us in total 1945. Okay, and so what do we do then? Then we divide 100 by 1945. This is 324 divided by 1940. So, and we go on. For this value, we have here 1,521 divided by 1,945. Okay, so this gives us the first Q. Okay, then we need to determine the coordinates. These are our coordinates, x and y. Okay, how do we do this? We do this by, I will erase all the rest here. We have an x-y coordinate system in which we place, as most advantageous as possible, our cocked hat. So for the first point of our triangle, we place it here, where our coordinates are 0, 0. The second point we will place on the x-axis, where we have 13 and 0 for y. And then we determine, we just simply measure it on our chart, what the position is of Q. Okay, so we just measure the coordinates here and the coordinates there, and this gives us then for the Q3 5.77 and 6.91. Okay, and then we simply just have to take our Q here and sorry for that, and then we multiply it. Okay, so we take 0, 0, we multiply it for the first point by 0.051. This gives us 0, 0, obviously. Okay. For the second point, we take 0.167 and we multiply it by 13 and 0. And this will give us then these coordinates here. And so for the third point, we do the same thing. Okay. And then, according to the formula, we have to add all these coordinates. So we add, it's a little bit complicated, we add everything in this row, this gives us 668. We add everything here, this is clear, this gives us 540, and these are then actually the coordinates of the most likely position in our cocked hat. Okay, so we have a coordinate here 6.7, which corresponds to this one here, and 5.4, which corresponds to that one there. Okay, this is our x and that is our y. Okay, and so this is actually a more sophisticated way of determining what the most probable position will be in our triangle when there is no uniform standard of deviation. Okay, remember once again, when there is a standard, when all observations have the same standard deviation, the same degree of error actually, as you can call it, we can simply just determine the median point in the triangle, or also called the Lemoine point, by this construction that I explained to you here, and then we get the most probable position, which is the Lemoine point, the Lemoine point. Okay. Voilà. So this is again then what you can do on your charts. You have your lines of position 1, line of position 2, line of position 3. You can determine the coordinates, you can determine the length of the sides. Okay, one point is considered to be 0, 0. The other point is on the x-axis considered to be, I don't know what it was 13, 0. This is to be measured on the chart. Okay, this gives you 577 and 6.9, which corresponds to what you see here. Okay, and then you simply just use this formula again here, which is actually, the notations are maybe a little bit difficult, but it's actually not so difficult to calculate your true position like this. Okay, voilà. Another way of talking about errors with regards to lines of position, with the equal probable errors with equal standard deviations, is the ellipse of uncertainty. Okay, in this case here you see that you have two lines of position, being this one and that one, with the same standard deviation. So you can consider this line of position as a band of position, as is said here, with the standard deviation on the one side, standard deviation on the other side. And then For the other line of position, you do the same thing, and then the most probable position will be somewhere here in this line on this ellipse of uncertainty that you can construct like this. Okay. There are also mathematical programs who do this for you. If you have something like star path or whatever, this is all based on mathematical calculations based on the ellipse of uncertainty. Okay, but again, this is not something that we will do in practice when we are calculating our lines of position. We'll not even do this. Maybe this is something you can do, you can construct, but in most of the time when we have a spread of an azimuth, we just say that we are somewhere in the center of our cocktail. Okay, this is maybe a little bit simplified, but well, that's the way it is. Now, let's talk a little bit about site planning. One of the challenges of celestial navigation is actually to prepare well for your sites, to make a good site planning. It's essential to get a good fix. What is a fix? A single line of position produces just what it is, a line of position, but if you have two lines of position, you can get a fix. Okay, I already told you earlier, when you have two lines of position, it's simple, then this will be your, or considered to be your position. But if you have more lines of position, you get a cocktail. Okay. Now, if we plan very carefully our sites or intercept, we will be able to reduce errors. Okay. If you plan your site, you should take some elements into consideration. First of all, when can the sites be taken? What bodies will be visible? How will we look for a good distribution that will give us the best fix? Okay. And in what order shall we take the sites? Okay. General principles of site planning, well, normally for bodies near the horizon or near to our zenith, okay, where the altitude is around 0 degrees or where the altitude is around 90 degrees. There it can be difficult, first of all, to determine the true altitude because of the refraction when we are at the horizon, or because of the principle of zenith distance when our altitude is 90 degrees. Okay, normally the principle of intercept is that we can mark circles of equal altitude. If this is your geographical position, you will have a circle of equal altitude with the zenith distance being the radius. But if your zenith distance is almost 0, then it's very difficult to draw these equal altitude circles. Okay. Now, all bodies can be observed during twilight, nautical civil twilight. For us, we use nautical twilight, except for the Sun and the Moon, of course, and Venus and Mars. In some cases, they can also be seen. The Sun, of course, always, but Moon, Venus, and Mars can, in some instances, on some dates, also be seen during the day. Okay. Now, why nautical twilight? Because during this period, it is dark enough to see the celestial bodies, but on the other hand, it's also light enough to have a well-defined horizon. When it's completely dark, you can't see the horizon, so you don't know what, you cannot measure the altitude of the celestial body. Okay. When it's too light, you don't see the celestial bodies, except for the Sun. So then it's also nearly impossible to do an intercept. Okay. Another thing to consider is the distribution of the bodies. Okay, I already told you that it's best to have a separation of at least a range of at least 180 degrees, which says that you should have a distribution of 60 degrees between every, at least 60 degrees between every true bear. Okay, if the lines of position are separated by only 15 degrees, you have much more uncertainty than, for example, when they are separated by 90 degrees. Okay, in this case, the ellipse of uncertainty will be much bigger. Okay, than when your bodies are or lines of position are distributed by 90 degrees. Okay. Another thing that we need to consider is the relation of the azimuth distribution to the systematical error. We already touched upon this a little bit earlier, but you know that good azimuth distribution can also can help you to cancel out systematic errors. Okay, like incorrect index and correction forwarding. Okay, if you look at this drawing here, in the first drawing, the azimuths are separated. These are the azimuths are separated always by 120 degrees. Okay, so this means that when you have to adapt your line of position, if this is your first line of position and you have to place it in direction or displace it in the direction of your azimuth, for this one as well, you do the same thing for the second line of position. You also do the same thing for the third. Where is my third line of position? Okay, it's that one here. So you will see that the angle that you get, or sorry, the triangle that you get will be much bigger. Okay, I think, I don't know, try to correct my drawing again because I didn't do it very clearly. So you get this line of position, you get that line of position, and then you get that line of position. And you see that if we compare it to this angle, that the new angle that we get is much bigger. So our most likely position will actually remain at the center of our old cocked head when we compare it to the new cocked head. Okay. If our azimuths are distributed by only 60 degrees, then we see that the same thing. When this was our initial position, but when we put the line of position, the first one in that direction, the second one in that direction, and the third one in that direction, we'll see that actually, if this is our new cocked head, that our old position isn't in the cocked head anymore. Okay, so then we have an outside most probable position. Okay, so you see that it's much more advantageous to use this observation distribution than to have distribution separated by 60 degrees. Okay, nevertheless, very often this is a system that is used in intercepts done by seafarers. Okay, another thing that we need to talk about is the order of observation. Okay, we know that during twilight the horizon remains actually well defined near the azimuth or the direction of sunset or sunrise. Okay, for a longer period, then it does 180 degrees away from that azimuth. Okay, so the normal thing to do would be to take sights close to that azimuth later during evening twilight and earlier during morning twilight. Okay, so for that you need to be able to calculate sunset and sunrise, but that is something that we will do later. Okay, but always keep in mind, if you take sights close to the azimuth, take them later when you're doing evening observations and earlier when you're doing morning observations. Okay, so in the morning you start with the observations in the direction of your azimuth. In the evening you end with the observations in the direction of your azimuth, because there the horizon will remain longer visible than on the other side. Okay. How to prepare for the sight? The first thing to do is to calculate, as I told you, sunset and sunrise or twilight, and then you pre-compute or determine the altitude and the azimuth of the celestial body that you want to observe. How can you do this? You can do this with the star finder, which you have learned to use last year, or you can do it with the sight reduction tables, which is a method that you will learn next year in the third year of navigation. Okay. Now the star finder, how to use it? You know that the star finder consists of first a basic sheet for the layout of the stars, which is this one here. Okay, and then you have transparent templates for the different latitudes. Okay, the instructions to use the star finder are there. You always start by determining the global hour angle of Arias. Then you subtract or add your longitude depending on whether you are in the east or in the west. And then you orientate the template that you use in the direction with this arrow in the direction of the LHJ of Arias. Okay, then you get something like this. And then if you want to do an observation, for example, here for Vega, okay, you can, first of all, on the outer ring, Vega is situated here somewhere. So on the outer ring, you can see that your azimuth will be 220 degrees. And for the altitude, you go to this ring, which is more in detail here. You follow the internal rings, and then you see here that you get an altitude between 60 and 55 degrees. Sorry, 50 degrees. This will give you an altitude of 55 degrees. Okay, so this is pre-computation of the azimuth and the altitude. Okay, voilà. Now, again, you select the stars by choosing a good azimuth distribution. This is not done. This is okay. Okay, you should at least have a spread of 180 degrees for all the azimuths. Okay, voilà. Then the work, you determine what stars you want to observe using this azimuth distribution. Here you have the approximate azimuth that you calculate via this, or that you obtain from the star finder. You have the approximate altitude, and then when it's twilight, you take your azimuth, you put it at an altitude of what you have found on the star finder, and then you look into the direction of 105 degrees, and then you should very easily find the star, and then you can calculate the height of your celestial body. Okay, this altitude you change into a true altitude. Okay, and you note down the chronometer time. Let's say it's I don't know what, 22:10 or so. No, 22:10, depending on what your location is. You calculate the azimuth with the ABC tables. Okay, and you can do this because you need your declination, you need your LHA, and you need your latitude for this. The LHA and the declination you can get from the nautical almanac here, because you know your chronometer time, which is actually GMT, or universal time, which is mentioned in the nautical almanac. Okay, so as I told you, you can transform HI into HV. HC you can calculate with a formula using, again, your LH, your LHE, your declination for the polar angle. I mean, not polar angle, or the LHE, the declination, and your latitude. Okay, this will give you then HC, and you compare these two, HV and HE, and this will give you then your intercept. Okay, for the first star, and then you do the same thing for all the other stars, and then you can get then you can start your drawing. Okay, voilà. You can also do this by using the site reduction tables, but as I told you, this is something that you will learn in the next year, the third year of navigation. Okay. Well, you see that the observation that you do with your sextant in this whole process is very important. Okay. You've learned how to use the nautical in the course of nautical instruments of the second year, I think. The first year you have learned, or you will learn, how to use the sextant, how to correct the sextant, how to correct the mirrors, etc., etc. If you want to learn more about this, or if you want to review this again, you should maybe check out this YouTube video, because it's actually an essential point, an essential element of your work. It's an essential element to try to reduce your personal errors as much as possible. And these are incorporated into your observation via systematic errors, over and underestimating of your observation. But it depends also what the effect of the random errors is when there is a bad weather or whatever, or when the horizon isn't very clear. It also depends on your experience in doing sextant observations, what the effect of the random errors will be on your observation. Okay, well, if you are very experienced, sites are expected to be accurate to about 1 arc minute, which is approximately 1 nautical mile. But as I said, this depends on your experience. If you're not very experienced, this can give you errors of up to 3-4 miles. Okay, voilà. So that's all for this week. This is a very short recording. Next week we will start talking about amplitudes, true amplitudes. This week is very short because I wanted to give you the opportunity. We have time, but I wanted to give you the opportunity to revise maybe a little bit of your navigation course, and to reserve a moment for questions. Okay, so tomorrow morning I will be behind my computer during the hours scheduled in the roster, so I will be there, and it is up to you. It is I will give you another possibility to ask me questions. If you have no questions, then we'll continue next week with the amplitudes. Okay, good luck.